So this presentation is on work that we've been doing on heated heavy oil storage tanks. We're trying to come up with very detailed information on the types of substances being emitted by the tanks, the nature of the emissions that were occurring, what impact the temperature, operating temperature of the tank had on these emissions, and what the variability between different operating areas was to some extent as well. So in this study we've actually looked at tanks in the Peace River area as well as tanks in the Cold Lake, Bonnyville, Lacorie area of northeastern Alberta. So we looked at 3 tanks in each of those areas, so 6 tanks in total. What we were trying to do was measure in real time the evaporation losses or venting losses from each of these tanks, monitor the composition and see how that varied with time. If there was any time dependence there, look at the types of substances that were being emitted in these streams. So we did on-site GC analyses to do real-time monitoring of what was coming off, but we also collected samples and submitted those to labs for very detailed analyses. And we looked at, there was concern about there being a lot of aerosols being emitted from these tanks. So if you are heating up a product and you volatilize some of the heavier compounds present in the product, and that gets into the atmosphere and cools, there is a potential for aerosols to form. And there was concern about being PAHs emitted from the tank, so we did the monitoring for PAHs as well as aerosols upstream and downstream of the tanks to see if there was any measurable particulate emissions and what the composition of those emissions would look like. One of the other things that we were wanting to do was to do a tracer test on the tanks, and the tracer test was really to understand how the plume would come off the tank, how it would disperse as it moved away from the tank. So originally we were looking at using sulfur hexafluoride to serve as our tracer gas, and since then we've actually changed our thinking on that, and we're now going to be using nitrous oxide and acetylene as 2 tracer gases. So nitrous oxide is a relatively heavy gas, acetylene is a relatively light gas. So if there's any density dependencies with respect to the tracer testing that would be done, then we would see that between these 2 different tracer gases. But we have the ability to actually measure both of those substances in real time at a rate of 1 hertz, so very frequent measuring of the rates at concentrations down to well below actual ambient levels of those substances, so we can very easily do these tracer tests. And so really what was holding us up in terms of completing that was to wait for these new analyzers to arrive, which have just arrived, and that's kind of where we're at now. So the detailed analyses that were done on the storage tanks, they looked at a variety of substances. We use a GC with a thermal conductivity detector to look at the typical fixed gases, oxygen, nitrogen, carbon dioxide. We had detection capabilities down to 50 to 100 ppm for those substances. We used a GC with a flame ionization detector to monitor for C1 to C4 compounds. And the detection limit for that was in the order of 50 parts per billion. And a gas or a mass spectrometer was used to monitor for all other heavier VOCs. And typically we would see compounds in the C5 to C12 plus range. Once you get much above C12, the vapor pressure of those substances is so low that they drop below the detection capabilities of our unit. But 10 micrograms per cubic meter for most of these substances is in the low parts per billion range for those substances. We use a sulfur chemiluminescence detector to analyze for reduced sulfur compounds. So this detector only sees compounds that have sulfur present in them. The detection capability of that instrument was 1 part per billion. So we're down near the odor threshold for a lot of these compounds with that type of detection capability. As well, with the GCMS work that was done, there was a number of analytical methods that were applied, TO15, TO17, and the PAMs, and each of these methods has inherent in it a series of compounds that you would be specifically targeting. So there's specific calibration gases you would use that have a range of what are deemed to be priority toxic compounds that would be detected by the system. So with a mass spectrometer, normally the way it works is the gases that are in your calibration gas become target compounds, and so you have complete confidence when you see those compounds that you're in fact seeing those substances in particular. And for other substances that aren't target compounds, that aren't present in your calibration gas, it uses a spectral library search to come up with a best match of what it thinks those compounds are, and reports those with a match quality. So when we do that on the gas streams that we were seeing from these different sources, we were typically seeing in the order of about 60 different compounds being produced, not including the PAHs, which were done using a concentrating technique where we would draw vapor samples, or in this case ambient air samples, through the traps that were used to concentrate the material, and then those traps were analyzed back at a lab, and the amount of material that was captured was measured and related to the amount of gas that was pulled through it. So we have much lower detection capabilities on that. The work that's been completed, we've done all the measurements in terms of the emissions measurements on the tanks that were part of the initial scope of work. We've as well measured casing gas emissions from 2 sites where there was casing gas venting taking place. The other sites didn't have casing gas venting. And we've prepared an interim report that presents all the laboratory results that have been compiled to date. So the outstanding work is really to do the 3 sets of tracer tests that were initially identified in the scope of work, and measuring the impact of operating temperature on the emissions from a storage tank. So in this case, what we're proposing to do is, in advance of going to the site, have a tank's heater turned way down, and then go to the site, install our monitoring system, and measure what the emissions are and how they change as we gradually increase the temperature, or the set point temperature of the tank heater. Additionally, during the first round of measurements, we happened to be at a site where a desanding event was taking place. So once we had finished our targeted measurements, we did measurements on what the emissions were during this desanding event. During that, part of the emissions exceeded our flow measurement capability. We got good data from it, but we didn't manage to capture the entire event, so it would be ideal to include another one of these events in the measurement work that we're going to do. So the measurement strategy, the liquid flow rates and temperatures into the tanks were monitored. We used Doppler and transit time flow meters to try and measure the liquid flows going to the tank. As well, we installed a microwave radar system to measure the liquid level changes in the tank. We put a transit time ultrasonic flow meter on the vent from the tank to measure the vapor flows, and we ran a sample line, a heated sample line up to that vent, and brought the gases down to ground level where we were using micro GCs to analyze the composition of the gas. And then we also used transit time ultrasonic flow meters to measure the gas flows from the casings where those were open and venting to the atmosphere. We had we monitored local meteorology during these testing periods to provide a record of what the wind direction was relative to where we had positioned our equipment and what conditions were like. So we set up a meteorological station at the site. And then we had our aerosol monitoring systems, which we used both an optical particulate monitoring device to measure PM 2.5 at upwind and downwind locations, and we used a high volume sampler to capture the PAH samples that we were also targeting for this work. So this photograph, or this slide, shows a photograph of a typical heavy oil storage tank facility. So this is a single well production battery. One of the wells is the primary actually the tank on the right receives all the production from the tank and or from the well, and the tank on the left was receiving the overflow from the initial tank. So we did our measurements off the first tank. And in this particular case, the casing gas that's being produced at this site, some of it is used for fuel for an electric power generator to generate electricity to run the downhole pump. And the balance of the gas is then put into the flow line that goes to the tank and would come off with the vapors that flash out of the product when they go to the tank as well. So in the foreground is the high volume sampler, and on the ground beside it is the optical particulate monitoring system. The white van has all our GCs in it. This is just a photograph showing the meteorological station that was installed to measure meteorological parameters. So we were measuring, again, wind speed, wind direction, ambient temperature. We didn't measure barometric pressure, though, or relative humidity. Here's where we're measuring the liquid flow in the line. So the advantage of using clamp-on technologies was we didn't need a port to, or any special arrangements to be able to measure these flows. The Doppler flow meter works on there being solids present in the oil stream and or bubbles that it can track the movement of. The transit time flow meter relies on the fluid being fairly clean with a lack of particulate matter or bubbles in the stream. And so if you use both flow meters, then there's actually a bit of an overlap between them where they can both see the same flows, but we were assured of seeing flows through one measure or the other, depending on the quality of the oil that was, and the nature of the oil that was going through the line. This is just a photograph showing the radar system that was installed on the tank. So we just used the thief hatch on the top of the tank and set the radar system on top, and had a radio transmitter and data logger that this was connected to that both powered the device and sent a signal down to ground level where we would retrieve it on our data acquisition system and be able to trend this and monitor it in real time. And this photograph shows the ultrasonic flow measurement system connected to the vent on the storage tank, and the initial part of the sampling system that was capturing the vapor samples from the vent and bringing a portion of it down to ground level for analysis. This is our data acquisition system at ground level. So here we're able to do real-time trend analysis of the different parameters that we're monitoring. This is the base station that the transmitters on the top of the tank communicate with, that's connected to the laptop. And here you can see the micro GCs that we were using to do a variety of different analyses on the gas streams or the gas that we were sampling. Just a closer up view of the GCs. This slide shows a variety of different things. It shows the flow rate of the gases coming from the tank. You can see that there's a fair bit of noise in this. This is the wind effects that are influencing the measurements that we're doing. The graphs below that show the continuous readings that we were getting for the analyses that we were doing using the micro GCs. So in both these cases, the dominant compound being emitted for these two different sites was methane. In the first case, the next most abundant compound being emitted was hexane, and in the other one it's ethane. So the difference was on this particular site 4, there was a modified production technique that was being used where they were injecting warmer fluids down into the well bore, and that was causing the liquids that were coming up to be much warmer and was influencing the nature of the gas composition. All the other sites we looked at tended to be more representative of this particular scenario where methane was most abundant and ethane was second most abundant. But the interesting thing to see here was that the compositions on an air-free basis are relatively constant. The heaters on the tanks are going on and off. They cycle. There's surges in the flow that's coming out of the wells. It's reflected in the graph above. So you would expect that there might be a potential for that to affect the composition of the mixtures that we were seeing, and really it wasn't. It was a very, very consistent vapor mixture that was occurring. So this table summarizes the actual total volumetric flow rate that we saw from each of the sites. We varied flows from, or we saw flows ranging from just over 1 cubic meter an hour up to 36 cubic meters an hour. And on an air-free basis, and a moisture-free basis, those same flows in terms of actual hydrocarbon vapors are given below, where we're seeing ranges of 0.67 cubic meters, or sorry, 0.11 cubic meters per hour up to as much as 28 cubic meters per hour of actual hydrocarbon gas being emitted. This table just summarizes the composition that we saw with the micro GC, so it characterizes everything in terms of C1 to C5 or C6 plus compounds, as well as CO2. So these composition profiles are on an air-free basis, and this just gives an indication of the amount of air that was in those samples. So normally the tanks that we were looking at were all free venting tanks. So when product's withdrawn from the tank, it brings air in. As the tank fills and evaporation losses take place, it helps to reduce the concentration of air in those tanks. So the tanks that had the highest concentrations were the ones that had the lowest liquid levels and the lowest vapor flow rates. The ones that had the lowest air concentrations were the ones that had the highest vapor flow rates and the highest liquid levels in the tank. The interesting thing to see here is really, if you look at the exception of Site 1, where there was a lot of CO2 being produced with the methane, the other sites are really producing what would normally be deemed a dry gas mixture. So this is not typical of a conventional upstream oil and gas facility. We're seeing extremely high values of methane and in relative terms very low values of non-methane hydrocarbons in these streams. The PAH analyses, the results that we get from this, if you look at the bottom, well, there's two types of data that came out of the analysis. So the sampling system had a filter paper that would filter out any solids that were in the airstream, and those were sampled separately, or sorry, analyzed separately. And then the gases that passed through the filter paper would then go through a polyurethane foam adsorption trap, and that would pick up the semi-volatiles that would have been present in those streams. And those would be analyzed separately, and then we would combine the two sets of results to come up with what the total aerosol analysis would be in terms of PAHs. And if you do that, you get the numbers that you see at the bottom. So in each of these cases, we positioned the upstream monitoring station really in the center of the facility, but immediately upwind of the tanks. And then the downwind monitoring system was typically placed on the berm that would surround the site. So it was usually an elevated location, and we could see with IR camera so that we were in the plume, and certainly in some of the areas you could easily smell the vapors from the tanks at the positions where we had the monitoring system. So we knew we had the positions of the monitoring systems well chosen, and so what we're seeing is that on average the concentration of PAHs in the downwind locations is greater than what we're seeing in the upwind locations, but it's really just barely above the background levels that we're seeing. So there are measurable emissions of PAHs. They're just not dramatically different than what we're seeing in the ambient air. The only exception where that didn't occur was Site 6. Site 6 happened to be the case where we were alongside in a couple of places we were actually near roadways which would have potentially influenced the upwind data, but there was a lot more traffic in this particular case. It was a busier roadway that was nearby, and I suspect that would be the reasoning why we've got the lower upwind, or sorry, the higher upwind values than we do downwind. So the detailed analyses that were done using the series of lab analyses I mentioned earlier, the results come out in a format that looks something like this. What shows up in these tables as you go through them is a lot of values that have zeros. These are compounds that were targeted by the analyses, and that's indicated in the match quality column by the value of a T. And the fact that we got a zero reading means that whatever was there, if it did exist, was below the detectable limits of the method. So there was no detectable amounts of these particular compounds that were being specifically targeted. So the zeros in here are meaningful, and so I've kept them in. I guess the other thing to probably look at that would be of interest would be the reduced sulfur compound analyses. Certainly in the Peace River area, there's been a lot of concern about odors associated with the operation of heavy oil storage tanks in that area. So the RSC in this particular column is the subcategory is a compound sublist, so that denotes that these are all sulfur compounds, which you can see that in this column where you've got the molecular formula, and each of these compounds has an S included in it. There was a lot of sulfur compounds that were targeted. We saw as many as 11 to 12 sulfur compounds showing up at individual facilities. Two of those actually were compounds that were not in the calibration standard, so they were not specifically identifiable as being a particular compound. We just know that based on their retention time and when they passed through the detector that they were different compounds coming through at different times. And the most abundant compounds that we saw coming off this in terms of sulfur compounds are H2S and one of these unknown compounds. And the rest of the compounds tended to be mercaptans and thiophene derivatives that were showing up. So I guess a summary of our observations to date, the vented gases are relatively low in non-methane hydrocarbons. So they're quite different than what you would see at a conventional oil and gas facility where you're handling conventional oil production or condensates. There are measurable PAH emissions associated with these facilities, whether they're coming from the tanks or whether they're coming from the fuel combustion that's taking place on site. It's not been determined, but in any case, there's clearly some contribution in terms of these types of emissions coming from these operations. There are noteworthy amounts of reduced sulfur compounds present in the vapors from the storage tanks as well as the casing gas from the heavy oil operations in the Peace River area. Most of the compounds that we saw that we were able to detect were well above the odor threshold of those compounds. So for example, the one example on the previous page, I believe the concentration of hydrogen sulfide was 32,000 ppm. So the odor threshold is 10 parts per billion, so we're well above that. Anyhow, thank you very much.